Hi everyone, this is Kiranmai from H&S department. Now in this session, we are going to discuss about an N-type extrinsic semiconductor. Under this session, we are going to have a derivation part regarding the carrier concentration of N-type extrinsic semiconductor, and then we will derive an expression for Fermi energy and how this Fermi energy varies with temperature and carrier concentration of N-type extrinsic semiconductor. So coming to an N-type extrinsic semiconductor, the fabrication of N-type semiconductors can be done by doping a pentavalent element to a pure semiconductor material. So after doping, what happens to the 5 valency electrons of the dopant? That means the impurity element. These pentavalent elements, which are having 5 electrons, the outermost orbit are added to the intrinsic semiconductor in small traces. Then the formed one is called as N-type semiconductor. So out of those 5 electrons, 4 electrons will be bounded with the semiconductor atoms and one is left free, which is weakly bounded to the parent atom. If you give even a Russell energy also, that fifth electron is ready to leave its parent atom and the atom will become positively ionized after donating the electron. Since this fifth electron is donating its electron easily, the pentavalent impurity is called as donor, and the energy level belonging to that impurity is called as donor level, and this donor level is very close to conduction band. And at room temperature itself, this donor level easily gives its fifth electron to the conduction band. Hence, the majority carriers of N-type semiconductor are electrons and minority carriers are holes. So from the figure on the screen, you can see that a germanium semiconductor, which is doped with a pentavalent arsenic element. Okay, arsenic, which is having 5 valency electrons. Out of those 5 valency electrons, 4 will get bonded with germanium atoms and one is very loosely bounded to the parent atom. Now on the screen, you can observe the energy level diagram for an N-type extrinsic semiconductor at 2 different temperatures. One is at 0 degree Kelvin, another one is at T degree Kelvin. So at 0 degree Kelvin, there is no carriers in the conduction band. Even there is a presence of donor atoms in the donor layer. Now, even if you give a small temperature rise also, the fifth electron of this donor atom readily donates its electrons to the conduction band by becoming positively ionized. By donating an electron, the atom will become positively ionized. So these atoms are positively ionized atoms after donating the electrons. So on the screen, you can observe one condition that at small temperatures, the number of electrons in conduction band is equal to number of ionized atoms in donor level. So this is the condition what we are supposed to use for the derivation of the carrier concentration of N-type semiconductors, which states that at small temperatures itself, the number of electrons in conduction band is equal to the number of ionized atoms in the donor level. So depending upon this condition only, we are going to derive an expression for carrier concentration of N-type extrinsic semiconductors. So coming to derivation for the carrier concentration, see for that, let us consider one semiconductor material which is having ND number of donor atoms. So the carrier concentration, the donor concentration here it is ND, and ED is the donor energy level, which is just below the conduction band. Okay, and at lower temperature itself, this donor level is filled with electrons. When you give small temperature rise also, these electrons will be excited to conduction band, and donor level will have more and more ionized atoms. So the density of electrons in conduction band according to intrinsic semiconductor, it is given by n is equal to 2 into 2 pi mu star kt by h square power 3 by 2 exponential ef minus ec by kt. This is the expression for number of electrons in conduction band. Now we have to get an expression for number of ionized atoms in the donor level. How many number of ionized atoms will be there? That is donor concentration into probability function. So donor concentration is Nd and the probability function is 1 minus f of Ed. Why? Because 1 minus f of Ed, because here we are talking about the presence of non-availability of electrons. So non-availability of electrons can be given as 1 minus the probability function. So f of E from Fermi Dirac distribution function f of E is given by 1 by 1 plus E minus EF by KT. Now 1 minus f of E is nothing but 1 minus of 1 by 1 plus exponential function. If you take this denominator into the numerator, you can write it with a power negative. Then this can be extended as 1 plus x whole power minus 1. The series will be like 1 minus x plus x square minus x cube and so on. So using that series, the first two terms will be 1 minus of exponential. Minus of minus will become positive. So 1 minus 1 plus e power e minus ef by kt. 1 and 1 will get cancelled out. So you are left with e power e minus ef by kt. This is the uh, probability function 1 minus f of e. Now in place of e, if you replace it with ed, then nd into 1 minus f of ed will be given as nd exponential ed minus ef by kt. So now we had a number of ionized atoms in the donor level and also the number of electrons in the conduction band. So at low temperatures, number of electrons in conduction band must be equal to number of ionized atoms in the donor level. So just equating both the expressions and getting exponential functions onto one side and constant terms on the other side, the equation will look seems to be on left hand side, it seems to be e power a by e power b. So you can write it as e power a minus b, that is equal to the constant. Again, a power a minus b kt, if you take kt as an LCM, you can convert the expression as 2EF minus of EC plus ED by KT, that is equal to this. Now, if you take log on both sides, exponential and log function will cancel each other. So the left hand side will be 2EF minus EC plus ED by KT, and the other side, right hand side, log ND by 2 into 2 pi ME star KT by H square power 3 by 2. Now get the KT from left hand side to right hand side, and then the negative term EC plus ED onto the right hand side, and then the multiplied term 2 onto the right hand side. So finally you will reach with a Fermi level expression, that is Fermi energy EF is equal to EC plus ED by 2 plus KT by 2 log ND by 2 into 2 pi ME star KT by H square power 3 by 2. So in this expression, if you place T equal to 0, that is at T equal to 0 degree Kelvin, the second term will completely become 0. Therefore, EF is equal to EC plus ED by 2. That means at 0 degree Kelvin, Fermi level lies in between the conduction level to donor level. The Fermi level lies in between conduction level to donor level at 0 degree Kelvin. Now again, to derive the carrier concentration of n-type extrinsic semiconductor, just take the final expression, number of electrons in conduction band, that is 2 into 2 pi mu star kt by h square power 3 by 2 exponential ef minus ec by kt, where you are going to replace this Fermi energy with Fermi energy equation. So before substituting them, just find out the exponential function, exponential EF minus EC by KT. And in place of EF, you are just replacing it with EF expression EC plus ED by 2 plus KT by 2 log ND by 2 into 2 pi mu star KT by H square power 3 by 2. This is EF expression what we had derived in the previous one. So just replacing them, this is EC by 2, this is minus EC, so you'll get minus EC by 2. So final expression will be like ED minus EC by 2, separating the terms by KT plus KT by 2 log term by KT. So you can cancel KT with KT. You'll get like ED minus EC by 2 KT plus half log term. Again, this half, this like A log B, you can write it as log B power A. So just taking this 1 by 2 from the coefficient to the power for the log, this will become like log nd by 2 into 2 pi mu star kt by h square power 3 by 2 whole power 1 by 2. Now this one is like exponential a plus b. So here you can apply the formula exponential a into exponential b. So this will be exponential ed minus ec by 2 kt into exponential log term. So again, exponential and log function cancel each other. So you are left with exponential function into a constant nd by 2 into 2 pi me star kt by h square power 3 by 2 power 1 by 2. This is the exponential function. Just substitute this with the density of electrons in the conduction band. So after substituting it, let's try like nd power 1 by 2, 2 power 1 by 2, and 2 power 1 and 2 power 1 by 2 will give you 2 power 1 by 2. This one is 3 by 4 and this one is 3 by 2. So a power 3 by 2 by a power 3 by 4, this will be like a power 3 by 2 minus 3 by 4. So this is equal to a power 3 by 4. So the final expression for the carrier concentration of n-type extrinsic semiconductor will be like n equal to 2 into nd whole power 1 by 2, 2 pi mu star kt by h square power 3 by 4, exponential ed minus ec by 2 kt. Now from this expression, keeping all the constant terms aside, small n is proportional to square root of nd, which states that the carrier concentration of n-type extrinsic semiconductor is directly proportional to square root of donor concentration. Square root of donor concentration. Now coming back to the Fermi energy, when you see the Fermi energy expression, EF is equal to EC plus ED by 2 plus log ND by 2 into 2 pi ME star KT by h square power 3 by 2 whole power 1 by 2. Now keeping this KT by 2. Keeping this at 0 degree Kelvin, so if EF is equal to EC plus ED by 2, so that means at 0 degree Kelvin, the Fermi energy level will be at the center of conduction level to donor level, will be at the center of conduction level to donor level. This is at 3 degree Kelvin. Now, if you increase the temperature, what happens? Slowly, donor atoms donate its electrons to the conduction band. So, carrier concentration and conduction level is increasing. So, the Fermi level will shift towards the conduction level. Once all the donor atoms get ionized, what happens? The shifting will become stabilized for some time. Even after that also, if you go for increase of temperature, the electrons from the valency band get excited to conduction band. The criteria is very similar to intrinsic semiconductor. Hence, the Fermi level will shift towards the intrinsic Fermi level. Now, if you increase the donor concentration, what happens? The shifting of Fermi level towards the conduction level will take little more time towards the conduction band, and then the criteria is very similar to the before, and the shifting towards the intrinsic level is same. So from the written part, you can see that as the temperature is increased more and more, donor atoms will be ionized. For a particular temperature, all donor atoms are ionized. Further increase of temperature results in generation of electron hole pairs due to breaking of covalent bonds, and the material tends to behave in intrinsic matter. So the Fermi level gradually move towards the intrinsic Fermi level. This is the variation of Fermi level with respect to the temperature and also the donor concentration. Thank you.